We'd like to find the derivative, and this is the function x to the x. Okay, this very much leads itself to logarithmic differentiation. So when we begin, okay, we take the natural log of each side, and then we use properties of logs to simplify. You see, otherwise, something like x to the x would be very difficult to tackle in terms of trying to figure out how to find the derivative. Okay, so here, when we have a power, and you know this is all inside the log, the power comes in front. And now we differentiate both sides. So we have to remember that the left-hand side is really a chain rule. Here, y is the inside function, and the outside function is the natural log. So we do the derivative of the outside, evaluate it at the inside, times derivative of the inside function, and then this side we can differentiate using the product rule. We have first times derivative of the second, plus the second times derivative of the first. So we have differentiated both sides of the equation, and now we are pretty much ready to solve for y prime. Well, this is 1 plus the natural log of x. I would multiply through by y, and then substitute our original y so that I have y prime as a function of x. And this is the derivative of x to the x. In this problem, we could definitely use other techniques. We could do a product rule followed by a chain rule. And this is how I did it in class. However, you could differentiate this using logarithmic differentiation, and we will to practice the technique. So again, we take the natural log of y. This is going to be the natural log here. And we have a log property about, well, here it's really the sum of three things. We could write this as ln of 3 plus ln of x plus ln of 2 to the 5x. Our property says something about if you have a product on the inside of 2, it's the sum of 2, but it also, you could show that if you have a product of 3 things, it would be the sum of 3 things, namely by, you could first do 3x and this, and then you could break apart the 3x just like this. Okay, now, one more step to simplify. This is the ln of 3 plus ln of x, plus we can bring down the exponent, ln of 2. Now this is much simpler to differentiate than doing a product rule and then a chain rule on the second function, because, well, this side, 1 over y prime. This side, the derivative of a constant, 0. Derivative of natural log, 1 over x. And this, if you look at it, it's x times 5 ln 2, which is a constant. So this is plus 5 ln of 2. Okay? Now we just multiply through by y, and we have 3x times 2 to the 5x multiplied by 1 over x plus 5, ln 2. And this would be our derivative. Of course, you could distribute, but this is the derivative. This is another in-class problem, which I just used the quotient rule when I worked through it. But one student used logarithmic differentiation, and I thought it would be a great example to do that way. I had to change it though and add dy dz, because looking at it, it's not clear if a is the variable or if z is the variable, and here a is just some number. Well, we have it as a base, so it should be positive and not equal to 1. And then we want to find the derivative of y with respect to z. Okay, and we will use logarithmic differentiation as an example of the technique, and there's nothing wrong with doing that although the quotient rule works well in this case too. Okay, so we take the natural log of both sides, and then we have ln of a to the z minus ln of a squared plus z squared. And then this turns into z, the natural log of a. And this is ln of y. Now, this is a great example to illustrate the fact that if you look at this term right here, there is nothing I can do. Nope. If we have a sum on the inside of a log, it does not simplify. There is no log property. Log properties are about quotients on the inside, powers on the inside, and products on the inside. So just be careful not to create your own log properties because you will get the problem wrong. Okay, so now we differentiate. And this is a constant, right? Here's a constant times z. So the derivative is just the constant. And then here, this is going to be a chain rule, where my inside function is a squared plus z squared. The outside function is natural log, so the derivative, we take 1 over evaluated at the inside, and then times the derivative of the inside function. And we are differentiating, with respect to z. Okay, well, now to finish the problem, we just need to multiply through by y. So y prime is then a to the z over a squared plus z squared times ln of a minus 2z over a squared plus z squared. Okay? If you do this using the quotient rule, as I naturally would, unless I was told to use logarithmic differentiation, it might look different than this, and that's okay. If you simplified from one to the other, you'd realize you have the same answer. I will do one more logarithmic differentiation problem. We have a function raised to a function. This is really saying logarithmic differentiation. So let's begin. I take the natural log of both sides, and remember really what this is. This entire thing is sitting inside the natural log. Okay, then when we have a power on the inside, it comes out in front as a multiplication. And we have the following. I'm just going to leave it like this. You could write this as sine over cosine and use log properties if you wanted. I'm not sure that would necessarily simplify things, but I will leave it like this. Okay, so then we differentiate the left-hand side as I have a few times, and then we differentiate the right. Now, this involves trig functions. We see a composition, we see a product, okay, but we can do this. So first, we'll notice that we have one function multiplied by another. So the first thing we will think is product rule. It's the first times. Now, derivative of the second. Okay, to get the derivative of this function here, that's our second function, we must use a chain rule where the outside function is the natural log. So we'd have 1 over, and then times, we multiply by the derivative of the inside function. Derivative of tangent, secant squared. Okay, so first, derivative of the second plus the second. Forgot my x. Times, and then the derivative of sine is cosine. We could stop here and at this point multiply through by y, which is tangent x to the sine x, and leave it unsimplified, which would be fine. However, you know, for the sake of practicing our trigonometry, I am going to make this a little bit more simple looking, because I see a sign, you know, tangent and secant squared. There will be some things that cancel out. So if maybe I will come over here. We will do a box where we just work on simplifying this. Okay, so I can rewrite this. Well, I know that secant squared is 1 over cosine squared, so I'm going to put one of them here. And one, I guess I will just leave like this. And then you see this is tangent x times 1 over tangent x. We are left with just the secant. Or you could write that as 1 over cosine. Okay, so that was this thing here. So let me go to the next step. This is all just the secant. And then this, there's not a lot I can do. And this was still 1 over y times y prime. At this point, I will multiply through by y. So I have tangent x raised to the sine of x times secant of x plus ln tangent of x times the cosine. Okay, there it is.